Okay, so we are going to continue talking about Newton and what he did with Kepler's laws. So, he really did a lot of work. He started, I think it's easier for me to explain at least, with what Newton did with Kepler's third law. Now remember, the third law said that for any planet orbiting the star, t squared over r cubed was the same. It was equal to a constant. So Newton wanted to come up with some explanation as to why this was happening. What was responsible for making the planets move around the sun in this way? And he knew that whatever explanation he came up with needed to fit inside of this t squared equals r cubed thing. So he did a couple things. The first thing was what we call Newton's synthesis. Okay, and so for his synthesis, what he said was that the same forces, or the same force, causes an apple to fall as... Just a second. The same force that causes an apple to fall makes us move around the sun, basically. This is where Newton and the apple thing, apple myth, kind of started. And he did this with a thought experiment. He said, okay, if we're on the Earth, on a very tall cliff, and we fire a cannon from the top of this very tall cliff, the cannonball follows a parabolic path until it hits the ground, which is great. Then he said, okay, let's take and expand this situation and make it just a little bit ridiculous. He said, imagine a planet kind of like the Earth, a round planet with a big mountain on top of it. And on top of this mountain, we're going to put the same cannon. Now, when we fire it normally, it follows that parabolic path, and it hits the ground. But unlike our little flat example over here, as the thing follows that parabolic path, the Earth curves away a little bit. So if we fire the cannonball even faster, it goes a little bit farther around the Earth. It makes it a little bit farther around. If we fire it even faster, it goes even farther around the Earth. And so Newton said, imagine a speed where we fire this cannonball fast enough, where it has enough sideways velocity, that as it goes around the Earth, it consistently misses the Earth. He said that is orbit. So in orbit, an object falls but constantly misses. Because it has a high sideways velocity. Okay. Newton called this orbit. He said this is what it means for a planet to go around the sun. As a planet goes around the sun, it's accelerating towards the center of the sun, but it constantly misses the center of the sun because it has a very high sideways velocity. And we'll look at a little bit of that, and I'll kind of give you a visual of it tomorrow. So, what Newton does when he's imagining these things, since he says it's the same force now that pulls the apple down and that makes us go around the sun, He's imagining what's happening to us in a circular orbit. So the first thing he does is imagine a circular orbit, and we'll look at the forces acting on a planet in circular orbit around the sun. So if we have the sun here, and the planet is in circular orbit around the sun, the only force acting on it would be from the sun, and that force would have to pull towards the sun. It's going in a circle, and we know that objects going in circles have centripetal acceleration. So we're dealing with centripetal acceleration and centripetal forces. So whatever force that's making the Earth go around a circle is acting in the same direction as a string that's tied to a ball that you pull around in a circle. So the net force is equal to mass times the acceleration of the object. That's a centripetal acceleration. And this force Newton called gravity. That was equal to mass times centripetal acceleration. Now, we know that centripetal acceleration is v squared over r. But if we're going to stay true to Kepler's laws, we need to use period. So we said, okay, we'll take and say that velocity is equal to the distance that the planet travels, 2 pi times its radius, distance that it travels divided by how long it takes to travel in that direction, which is just the period. So Newton makes this substitution, and it says, okay, we have 4 pi squared r squared over t squared times m divided by r. That's what that whole side comes out to be. One of our r's goes away, and that's going to be equal to the force of gravity. And he had to do some thinking about this force of gravity. Now, he knew for this force of gravity that it had to do with the mass of the planet and the mass of the object we're talking about. Just like weight has to do with the mass of the object in question. I have more weight than a smaller person because I have more mass than a smaller person. But he also figured for a planet it had to do with the sun. So it had to do with the product of the masses. And he saw an R, and this is kind of the genius of Isaac Newton. We have an R here, and if I'm going to get an R cubed quantity, I'm going to need to have R squared on the bottom here. So he knew the force of gravity was going to look something like this. Now, mass of the big object like the sun, mass of the planet, distance between them squared. Now, if this were what the force of gravity were equal to, then a 1 kilogram object, a 100 kilogram object away from another kilogram object that's only a meter away would experience a force of 10,000 newtons. That's way too much. So what Newton did was say that there is some proportionality constant, G. It's a factor to adjust the size of gravity down to what it needs to be. So we call it the gravitational constant. Newton didn't know what this number was, but he knew it had to be small. Because if I put two weights next to each other, I can't actually measure their force. So Newton came up with this thing, and he had, all right, G times the mass of the sun times the mass of the planet divided by the distance separating them squared was equal to the mass of the planet times 4 pi squared r over t squared. When you rearrange everything, these r's don't cross out. When this r goes down here, you get r cubed over t squared is equal to, these masses go away, 4 pi squared over gm. And this is what Newton came up with. The question was, does it fit with what Kepler did? So, this 4 pi squared thing pi is a constant, and 4, the number, is the same no matter what planet you go to. G is a gravitational constant. It never changes. And the mass of the sun, well, each planet goes around the mass of the sun. So this formulation is true for all planets. What Newton said for his force of gravity was true for all planets, and it helped to explain why they were going around in these fixed harmonies. So Newton had done it. He had come up with at least an explanation for gravity that was mathematical, that could be used to predict how things moved by using Kepler's third law. This is the big deal. Okay, so we call this Newton's universal gravitation. Universal gravitation. It's universal because it can be used anywhere, not just on Earth, not just in the heavens, but anywhere. So universal gravitation is the force of gravity is equal to G, this gravitational constant, times the mass of one object times the mass of another object, divided by how far apart those two objects are squared. We will play around with this a little bit. Force of gravity is really easy to calculate, and the nice thing about the force of gravity is that it is always attractive. We haven't found any new crazy types of mass that are repulsive yet, so for now the force of gravity is going to always, always, always be an attractive force. And again, we'll play tomorrow a little bit with what this r squared means in calculations. And we'll talk a little bit more about just putting this into your calculator, because the numbers we have to use, it turns out, are incredibly large. So, we're going to take a break from Newton and go back to Kepler really quick and talk about the second law. Kepler's second law, the law of equal areas. Now, we are not going to go into Newton's proof here, but he invented calculus and did something called the conservation of angular momentum. Conservation of angular momentum to explain the fact that that an object going around the sun was faster when it was closer to the sun and slower when it was farther away. So if we take this simple diagram, we call this radius A to the closest point, and then over here to radius B. And we're going to have a velocity at radius A, velocity A, and a velocity, oops, drew that too big, and a velocity at radius B. Now, Kepler's law said that the velocity at A was going to be greater than the velocity at B. Newton said that this conservation of angular momentum explained why. So really all that you have to do to compare these speeds is say the velocity at A times the radius at A is equal to the velocity at B times the radius at B. It's a very simple relationship that shows how that velocity changes based on the radius. This quantity of velocity times radius times the mass of the object stays constant as it goes around, but the mass crosses out. So this is all we have to do to compare the speed of an object in orbit at different points. All we have to know are the radiuses. Very simple, very straightforward, I think. With the third law, the calculations are just as easy. We say t squared over r cubed is equal to t squared over r cubed. So let's pick an asteroid. And let's say that with our telescope for our asteroid, we know that the period of the asteroid, let let's see. We know that the period of this asteroid that we happen to see going around the sun is 4 years. And what we want to know is, based on this period of 4 years, how much farther away from the sun is this asteroid than we are? So this gives me the asteroid's information. I know that the period is 4 years. We're going to square that, and I want to know the radius. But I have to compare that to something else. And what makes Kepler's laws nice is that we can use the Earth. The asteroid goes around the sun. The Earth goes around the sun. So for the Earth, our period is 1 year. You know what's a fun number to square? 1. And what we're going to say is that our radius is 1 astronomical unit. We are a distance of 1 away from the sun. We're going to measure everything else in relation to that. So we'll plug that in on the Earth's side. We have 1 squared over 1 cubed. 1 squared is 1, 1 cubed is 1. So we have 1 equals 16 over r cubed. So we get r cubed is equal to 16. When we put that into the calculator and find the cube root button, because really that's the only way to do this unless it's a nice number, this one doesn't happen to be a nice number, we see that the, let's say r is the cube root of 16, plug that in, and the radius comes out to be roughly 2.5 astronomical units. So this asteroid is 2.5 times farther away from the sun than we are. And we can get that just knowing information about the asteroid's period and comparing it to the Earth's period. In class tomorrow, we'll talk a little bit about Cavendish, and we'll do a little bit more work with these calculations.